All right, everyone, we're going to shift gears here now and talk about what happens to charges on the surface and in the interior of conductors. Now, when we're talking about these charges, we're not talking about all of the charges that are in these conductors. We're talking about the excess charges. So let's say, for instance, an object has 1,000,000 protons. Well, maybe it's got 1,000,005 electrons. Or it's got 16 protons. Well, maybe it's got 28 electrons. It's got extra electrons. We want to know what happens to those extra electrons in a conductor. Why a conductor? Well, we don't usually talk about this in the context of an insulator because the charges in an insulator don't move around that well. When we're talking about a conductor, the charges can go pretty much wherever they want as a result of electric forces. They can't do that so easily in an insulator. So we're going to talk about this mainly in the context of conductors here. You've got to define a term here first. Static equilibrium. Equilibrium means what? You guys have seen that before, right? Biology class, you've seen equilibrium. Even in physics 20, we talked about equilibrium. Equilibrium means balance. Static equilibrium, balanced forces when something's at rest. So when we talk about static equilibrium in the context of charges, it means the charges are all at rest. These extra charges, these extra electrons, push each other apart. If you've got 5 extra electrons in a conductor, then they will each repel each other. And they're going to go all over the place. But at some point, the forces will end up balancing. When the charges get to just the right place, the forces will balance. That's when the electrons are in static equilibrium. The forces are balanced. When we have a conductor, and when we have electrons on that or in that conductor, the electrons will eventually always reach a point of static equilibrium because they're free to move around as much as they want. And at some point, just by chance, they'll get to the right place where the forces balance each other. The repulsive force on one electron is balanced by the repulsive force of another electron. So the first thing you got to know about what happens to these charges is that they'll reach a point of static equilibrium. They'll move around as a result of repulsive forces between each other until the forces balance, and then they'll stop. That's the goal, and that's what's going to happen when we're talking about excess charges in conductors. Now, the first shape we're going to take a look at, everyone, here is when we have what we call a solid conducting sphere. What does that mean? Well, it's like a marble that's made out of steel, or a marble that's made out of copper, some kind of conductor. Let's say in this case we have extra electrons, 3 extra electrons. Now, that might mean that we have 5 protons and 8 electrons, or it might mean that we have 1,000,000 protons and 1,000,003 electrons. The same analysis that we're about to perform could be performed if we had 50 extra electrons or 500,000 extra electrons. It would just be a lot of lines and a lot of stuff on a diagram that might clutter it up. It would be harder to see, but it would be the same analysis. All right, so we have these 3 charges here, these 3 extra electrons. We'll call them charge 1, charge 2, and charge 3. Charge number 1 will experience 2 forces here. It's going to experience a force of repulsion as a result of number 2. That's going to push it down this way. It's pushed away from number 2 this way. And at the same time, it's pushed away from number 3 this way. Those 2 forces create a net force on this object, on this charge, that's this way, in between. All right, does that make sense? If you got a force that's this way in the direction of this red arrow and this way in the direction of this red arrow, then the net force will be midway between those 2. Now, similarly, we're going to have a couple of forces acting on the second charge there. There's one force caused by number 1 that pushes it up this way, another one caused by number 3 that pushes it this way. The net force is going to go up the middle. And finally, the third one, same deal. We got a force caused by number 1 this way, force caused by number 2 this way. The net force goes in between them, right up the middle that way. So each of these extra electrons experience a force outward. What happens to these electrons as a result of that outward force now? Well, when you're pushed outward, where do you go? Out. These electrons go outward. They get to the surface, and then they stop. Anybody tell me why they don't go beyond the surface? Why this little electron here, when it gets to the outer surface there, stops there? I'll give you a little hint. What is this solid conducting sphere most likely in? Like, what's surrounding this solid conducting sphere? Probably, anyways. Somebody said it. Air. Stephen, was that you? Air? Okay. Air is a good example of a what? Versus copper, which is a good example of a... Good. Air is a good insulator, typically at least, unless it's damp. Air is a pretty good insulator. That means when these electrons get to the surface, they move through the conductor easily. They're pushed away from each other. They move to the surface. But when they get to the surface, they want to go into the air, but the air is an insulator, so they can't keep going into the air. They stop at the surface. So there's two things that you're going to learn from this. Number one is, when these extra electrons are in this conducting sphere, they will go to the outside. They'll go to the outer surface. Number two, what do you notice about the spacing here? Okay, good, good. They go to the outside, and they're evenly spaced on the outside. So in the end, the final diagram looks something like this. The extra electrons go to the outer surface, evenly spaced. These little blue lines that you see drawn here in the second diagram just represent field lines. Okay, they point inwards, of course, towards negatives. Now, if we had 1,000 electrons, the same thing would apply, except you'd have a little bit more complicated of a diagram showing 1,000 electrons evenly spaced around the three-dimensional sphere that we have here. But what if we have something that's a little bit flatter, or a lot flatter? Something that looks like this. Let's name these guys charge 1, charge 2, and charge 3. These three charges are randomly distributed right now. They want to reach a point of static equilibrium. They're not there yet. The forces aren't balanced yet. So how do they reach it? Well, let's look at charge 1. It experiences two forces as a result of the other two. It's repelled by number 2. Okay, number 1 is pushed by number 2 to the left. And it's also pushed by number 3 to the left. Anybody explain to me why the force of 3 on 1 is smaller than the force of 2 on 1? Yep. Good. It's a bigger distance, right? So F is inversely related to R squared. Bigger distance, smaller force. Bottom line is, those two repulsive forces end up combining to give me this one. Look over here. The force on number 3. It's pushed away by number 1, and it's pushed away by number 2. Why do they combine to give me a much smaller force than this one? Why is the force of 1 on 3 and 2 on 3 smaller than the force of 3 on 1 and 2 on 1? Okay, Lucas has got it for us. Yeah, again, it comes down to the distance, as Stephen said in the last one, right? The distances are bigger, the force is going to be smaller. Okay, finally, this is the one that we're really concerned with here. The force of 3 on 2 to the left is smaller than the force of 1 on 2 to the right. And that should make sense to us. Last people said, Stephen and Lucas both said, bigger distance, smaller force, right? We got a force to the right that's bigger than the force to the left. All right, we're there. What happens to that charge now as a result of that bigger force? There's an extra electron that isn't in static equilibrium right now. It wants to go to static equilibrium. The forces aren't balanced. What happens to this electron as a result of this guy being bigger than this guy? You know this. You know the answer to this. Aaron, what's going to happen to it? If the force to the right is bigger, what's going to happen to it? It's going to move to the right. As it moves to the right, what happens to the value of this force right here? Better? It gets smaller. What happens to this force right here? Good, it gets bigger. At some point, they're going to balance, right? At some point, this is going to be small enough, this one's going to be big enough to balance each other. Where do you think that's going to happen? Where do you think this charge right here is going to be when these two forces have balanced out? In the middle. Yeah, in the middle, between 1 and 3. So what you end up with here is, although it's a different shape, pretty similar result as what we saw in the last one. The charges go to the outside surface, and they're evenly spaced. Outer surface, evenly spaced. Got it? Outer surface, evenly spaced. This one looks complicated. It is a little bit. This is where we have what we call an irregularly shaped object. In other words, a pointy object, like your finger. It doesn't have to be a needle pointy, but your finger is pointier than your cheek. Okay, that's what we're talking about with something that's pointy here. They've got 4 electrons drawn here, but we're going to get rid of one of them because we don't need the 4th one. Although we could draw it with 1,000, it would just be more complicated, that's all. We're going to call the first one number 1, number 2, and number 3. Number 1 pushes number 2 this way. Number 3 pushes number 2 this way. Now we got a 2-dimensional thing. Let's resolve that F32 into components. So we don't have to do any math. Don't worry about that. Let's call this the y component and this the x component, even though it's not truly x and y axis here. The y component of F32 pushes that electron to the outer surface. So again, for the 3rd time in 3 diagrams, where does the electron go? To the outer surface. Doesn't go beyond that because air is an insulator. So far, all of our excess charges, no matter what the diagram, always go to the outer surface. All right, take a look at this red F12 and this x component of F32. Which one's bigger? The red force pushes it out to the tip. The green force pulls it back from the tip. Which one wins? Fraser, which one wins there? The red one or the green one? Have a look. Okay, pay attention. The red one or the green one here? Which one's bigger? F12 or the x component of F32? Good. F12 is bigger. So it's going to go towards the tip. And at some point, this is going to get small enough that that's going to balance with that. But this is what it's going to look like when it does. These electrons are now on the outer surface, but not evenly distributed. They're closer together at the tip. The result is that we get a higher concentration of electrons at the tip of something than we do along the smooth surface. You walk across the carpet and you go to shock somebody. What do you do when you go to shock somebody? Walk across the carpet, stick out your cheek to shock somebody. I guess it depends upon who you're trying to shock. You might shock somebody by sticking out your cheek towards them. But normally, if you want to electrically shock them, what do you stick out? Your finger, right? It's because there's a buildup of charge on your finger that's not built up on your cheek, because your finger is pointy. You get a higher concentration of charge on pointy things than you do on smooth things like your cheek. Okay, it works even better when we're talking about things like metals, which are better conductors than our bodies are, right? That's why we have a lightning rod, right? Why are lightning rods sharp? pointy things as opposed to rounded things. Because there's a higher concentration of charge on a sharp pointy thing than there is on a rounded thing. It attracts lightning better. Right? Just like your finger attracts that shock better. Okay, tomorrow we've got one or two more diagrams. One more diagram. We'll finish that up tomorrow, and then we'll pick it up from there. That's it for today.